in the lab, Twitch stream glowing, formulas flashing, minds wide, knowledge flowing, equations on the board, numbers never sleep, teaching math and physics while them haters count sheep. Actual education, tune in and get schooled, flipping textbooks, breaking all the rules, from Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex, quantum theories on deck, breaking all the specs, relativity theories, worlds getting small, grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep, grazing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold, brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice.
Alright, what's up everybody? The queue is empty for a change. Yes. Love an empty queue. Yes, today is Wednesday. I think I'm gonna have to do another office hours tomorrow though, honestly. Because we have our first midterm for my physics class on Friday. And usually I do open up like more office hours on the week of an exam so that people can ask more questions. So I think I'll have to set one open for tomorrow. And then I want to see about doing a chess tournament on Friday, but I just got called in for a work meeting in San Francisco on like Monday, so I might fly out Friday. I don't know. I'm debating it right now. Trying to figure it out. That's why I've been hesitant on announcing Friday's activities yet. I might have to fly out for that. Glad to see they solved that wire straw substitution. It was very cool. Yeah. The second someone pointed that out, I forget who it was. Maybe it was Breasticles, because Breasticles is one of the first people to show me the wire straw substitution. But yeah, once you do that, it's actually not that bad of an integral. It's actually quite cool. I remember we were reading it. Apparently it's called like the sneakiest substitution trick in like all of calculus. Find it. Where is it? There we go. According to Spivak, this is undoubtedly the world's sneakiest substitution. It's really sneaky. Very cool though. So yeah, anytime you have something of this is something else. This is what we were doing during class actually. Anytime you have something that's just a function of like sines and cosines, I think, right? You can do this substitution. Let me derive like actually where this comes from, right? So if you say that t is equal to tangent of theta over 2, is that a half angle substitution I need to use then? Probably is. Okay, yeah, there we go. Here's some fun ones. I'm just curious how this works. So if t is equal to tangent of theta. Okay. So you're saying t is equal to sine of theta over 2, which is also equal to cosine of theta over 2. Maybe viewers are missing my interesting questions. Well, the first hour, Kaushik, has to be technically open for the physics students for the UCLA class I teach. Yeah. But we did do one of yours. And actually, they don't get missed. One of the awesome people in our Discord, Narosky, saw it in the queue, and he answered the one about the geometry stuff. I want to see how this one works, though. How do I show that cosine of theta is equal to that? Ha. Okay, so if t is equal to tangent of theta over 2, I guess I could reverse engineer it, right? Is that kind of what's going to happen? I wanted to see where maybe this comes from. Oh, maybe I see it. Okay, wait. Use the Euler? Yeah. I don't want to have to. I know that's the Zach one, dude. What's up, Jeff?
My name is Jeff.
Let's just do this. So I think what sine of theta over 2 is equal to. I don't really think I care about this parity. Let's say 1 minus cosine of theta all over 2. Okay. So t is equal to the square root of 1 minus cosine theta all over 2. And then... Wait, no. Okay, that's for sine. And then cosine... Okay, I see what this is. Because then cosine of theta over 2 is equal to the square root of 1 plus cosine of theta all over 2. So I can replace that with here. So then this is 1 plus the cosine of theta all over 2. And then I think I see what I want to do. I'm going to square both sides, right? Well, the 2's are going to cancel, which is nice. Those go away. I'm going to square both sides. And I'm going to get that t squared is equal to 1 minus cosine theta over 1 plus cosine theta. This gets me closer to an expression for cosine, right? Okay, because then I can just move this over. So t squared plus t squared cosine theta is equal to 1 minus cosine theta. I see what's going to happen. Okay. I'm going to, move that. So then I'm going to get t squared cosine theta plus cosine theta is equal to 1 minus t squared. And so then this is now cosine of theta t squared plus 1 minus t squared. So cosine of theta is equal to 1 minus t squared over 1 plus t squared. And I think that's what I saw, right? Yeah, there you go. Cosine theta is 1 minus t squared. Okay, cool. That's very cool. All right, so that's how that one pops out. I want to guess... okay, so then how do we get to the tangent one, though? Or sorry, how do we get the sine? Well, I know that 1 minus cosine squared is equal to sine squared. Maybe that'll help us out. Let's see. I'm curious. Okay, so 1 minus... So first of all, let's square both sides, right? So cosine squared theta is equal... This is going to be 1 minus t squared squared over 1 plus t squared squared. And then I'm going to do 1 minus... Because then 1 minus cosine squared is going to get me sine squared. And then, okay, so this needs to be 1 plus t squared if we want this to have common denominators. This needs to equal 1 plus t squared squared minus 1 minus t squared squared. Oh, very cool. And then this is all over 1 plus t squared squared. Uh-huh. And I think we're gonna do maybe this is a difference of squares. Is that how it's gonna work? Well, I don't think so. Maybe actually. Yeah, wait. I can rewrite this as 1 plus t times 1 minus t. No. Yes, it is a difference of squares. This is a difference of squares. Yeah, right? Difference of squares. That's very cool, right? If you have a squared minus b squared, that's also equal to a plus b, a minus b. Very cool. So then this whole thing becomes 1 plus t squared times 1 minus t squared all over 1 plus t squared squared. Okay, one of those is going to go away. Wait, but now I'm left with 1 minus t squared. 1 plus t squared is equal to sine squared. Wait, he says check that numerator. Yeah, did I fuck up the numerator? One sec, let's see. Alright, we agree cosine theta is 1 minus t squared over 1 plus t squared. Square both sides. Cool. 1 minus t squared squared. 1 plus t squared squared. 1 minus, so that becomes 1 plus t squared squared minus 1 minus t squared squared all over that. This is a squared minus b squared, so it's a minus b. Oh, I see. I see where I messed up. I see. Sorry. This whole thing here is a, and this whole thing here is b. Haha. Okay. It's not just a times b. Yeah, got you. Okay. Gotcha. Okay, so this thing right here is like A. And this whole thing here is B. Yeah, I messed that up.
Oh no.
Hell no, man. What the fuck, man?
Okay, so this is 1 plus t squared plus 1 minus t squared. That's like the a plus b term. And then you're going to have 1 plus t squared minus 1 plus t squared. Right? Okay. Now, okay, t squared minus t squared cancels, so I get 2. And then this is the 1 minus 1 cancels, so that's going to be 2t squared all over 1 plus t squared squared, but that was all equal to sine squared. So then I can square root both sides. Brilliant. Oh man, but wait, I'm gonna get a square root of 2. I don't want a square root of 2. Fuck. We lost a 2. We did lose a 2. Where did we lose our 2? How did we lose it? Okay, let's make yeah. A plus B. Yeah, I agree there's supposed to be another 2t. I want to know where that is, though. Ah, yes, you are right. Sorry, there's a 2 from here, and there's a t squared plus t squared. So that's actually 4. Thank you. Correct. Forgot to add these two together. Yep, good job, guys. So that's going to give me 2t over 1 plus t squared is equal to sine of theta. Very sneaky. Okay, that's cool. Okay, so I've proven these parts to myself. What about the d theta, though? Okay. So, if t is equal to tangent of theta over 2, then dt is the derivative of tangent of theta over 2. So the derivative of tangent is secant squared. So I'm going to say secant squared theta over 2, and then times the derivative of what's inside, which is going to be 1/2. And then there's a d theta on there as well. Okay. Ah, but now here's the clever thing, right? Secant squared of theta over 2 is the same thing as 1 over cosine squared of theta over 2. And that's we're going to use this identity. Okay. That's pretty cool. Okay. So this is equal to 1 over the cosine squared of theta over 2. Still a 1/2. Then a d theta. And then cosine squared, we're going to flip this. So that's 1/2. Radical goes away. We're going to do 2 over 1 plus cosine of theta. D theta. 2's cancel. Okay. So then I have d theta over 1 plus cosine of theta. And then I think I'm going to use my identity for cosine of theta. Right? I already said that cosine of theta was equal to this. I think that's the way I want to do it. So let's see. That's d theta over 1 plus 1 minus t squared over 1 plus t squared. So let's combine denominators here. Beautiful. So then these things will cancel. And we're just going to get d theta over 2 over 1 plus t squared, I think. So is it 1 plus t squared? Okay, close, guys. This is dt. Beautiful. So then I just multiply this to the other side. And I'm going to say that d theta is now 1 plus t squared all over 2. No, 2. Sorry, I have it flipped. 2 over 1 plus t squared dt. I think that's what we had. Yes, nice.
Good job.
Yes. Nice. Okay, we proved the Weierstrass substitution. Yeah, awesome. That's cool. Glad we did that. Very cool. Okay. I at least understand where it comes from. I do need to hydrate. Thank you, Sensation. I forgot to turn off the Sammy core during my lesson today. Sammy's what connects the rewards to my OBS. And dude, you hit baby voice.
Not good.
And that's where, like, yeah, I saw you in the text. You're like, he's going quiet. I'm like, yeah, because I have to go manually turn off that sound filter now. Otherwise, the kids are going to hear me with a baby voice during Twitch, during the lesson, dude.
Oh shit, not good.
Like, what's going on?
Hell no, man. What the fuck, man?
I appreciate it. It was funny. But that's why I was quiet, because I was going into OBS trying to figure out how to disable baby voice manually rather than wait 30 seconds. You can redeem baby voice right now if you want. I'm actually curious if it still works or if I broke it. Anyways, yeah, this was really fun. Boom, boom, boom. Actually, also big news. I was just checking, like through some of the questions were being asked here. We had some fun ones from yesterday. Let's see.
I pressed because I thought they weren't using Twitch, and I thought the paradox wouldn't be funny. Yeah, no. But yeah, so that redemption on Twitch changes my entire OBS, and so anything that's streaming out through OBS will end up getting the effect. Usually, what I do to prevent this is that when I start teaching for the morning classes, I disable the bridge connection, but I forgot to disable it this morning. So thank you for reminding me, because I saw that.
Because I get an audio cue that baby voice is being redeemed. There's like a big baby voice that I hear, and I was like, oh shit. I was like, I forgot I had this turned on. So it's a good thing you did it, because otherwise someone else could have redeemed something else, and then it would have been bad, you know. I don't know. So, did a good job. Okay. It was funny. Yeah, I had some funny. I was posting this in our Discord today. Someone Someone asked me if they could get an extension on their homework today because their cat had to go to the vet due to having extreme diarrhea, and they work in the mornings, and so they weren't able to get to it. I'm like, oh dear. I am 100% gonna. At least their English is up to standard, correct? Yeah. I'm at the end of whatever, when I decide to stop teaching at universities and stuff, I'm gonna come up with a little book of all the ridiculous emails I've gotten from students over the years. They're really funny. I just chuckle. I laugh at them sometimes. In this case, I gave the student an extension because it's like one of the first homework assignments, and honestly, like Kuda's been fucking up so much. It's not really their fault. But I will say to this student, if you're watching, they get a full week to do these assignments. Like, I give massive due dates on things. So if you wait until the last minute and then, yeah, poor, like, whatever your cat's name is, Fido, Alfalfa, or whatever, gets diarrhea, like, yeah. It was good and shit. We was Kangs. My cat be mad fucked or something. We were Kangs, dude. I love that one. That's such a good meme. we was Kangs and shit. Yeah, they're just funny. Bless them. Bless those children. They went through some rough times, so I understand. But yeah, it's a new take on the my dog ate my homework. Yeah, because all the homework's digital, so dog can't really eat your homework anymore. But if I really wanted to be a stickler, I could say, show me like a note, show me a receipt, because I know there's a receipt. Yeah, I know that costs a lot of. If you actually went to the vet, that's never a cheap thing. Show me a dated receipt of you having to go take your cat to the vet. Show me a dead cat? No, not that bad. Let's maybe see this one. I'm curious about this one. This was an extra question that got asked. This was from Ukashik Techno. The largest non-negative integer for which the limit as x approaches 1 of this is equal to a quarter. Oh, so the integer is a. Tomorrow's gonna be horrible. Oh no. Do you guys have a heat wave coming in? Ew. 30.
Oh, brother, this guy stinks!
I guess, yeah, it's pretty chill now. But then... Oh man, yeah. Come 4 o'clock in the afternoon. 30 degrees Celsius. That's quite warm. What is it gonna be like in London, though? London's usually the hottest country, right? Because it's all the concrete. Where's just like London, dude? What, like London, England, dude? Okay, maybe like London King's Cross. Let me see. Okay, whatever. This is being weird. There we go. Okay, London's gonna be a high of 94. Tomorrow. That's pretty hot. Especially for a place that does not have air conditioning. Yeah. Okay, let's see this one though. Integer, for which is equal to a quarter. Fascinating. Limit as x approaches 1. Well, okay, so I'm just gonna plug in 1 for a bunch of stuff real quick, right? Can I just do that? All right, what is this? This is negative a plus the sine of 0. No Mr. B tonight. I hope he didn't get another sunburn. Yeah, that poor guy. Okay, plus a. Well, I already see kind of an issue here, right?
Brother, this guy stinks!
Because this is going to go to 0. This two things are going to go to 0. So we're already kind of screwed. And then what? This is x plus... Or sorry, 1 plus... Sine of 0. Minus 1. I see. So you already get an issue here if you get 0 over 0. And then this is all raised to the root of 0 over 0. Okay, so we got a lot of 0 over 0s happening. This is troublesome. Troublesome for sure. My gut instinct is to do L'Hopital's, but I don't know how L'Hopital's works when you have like a root on the top. Oh man. What shall you do? I mean, I think maybe like the root test for like convergence, because this is a limit to me, right? It's kind of like my next thing. No, but that says n goes to infinity. Which, I mean, this is kind of going to infinity, right? Because it's going to 0 over 0. Okay, maybe we need to evaluate things piece by piece. Like, let's evaluate what this would be. So what's the limit as x approaches 1 of 1 minus x over 1 minus x to the 1/2? Right, this is indeterminate because this is 0 over 0. So we don't like that. So I could take the derivative of each side, right? Top and bottom. See what we get. And so for here, I get 1, right? Because derivative of minus x is... Oh, derivative of minus x is minus 1. Wait, so this is 0. Derivative of this is 1. So you get negative 1 over 0. And that's going to be minus 1/2 x to the minus 1/2. Oh, so that's not so bad, right? So that's going to be negative 1 over negative 1/2, right? As x goes to 1. Okay, so now this is actually kind of chill. So this is equal to 2. Okay, so this thing goes to 2, right? Can we assume that? Assume that this goes to 2. I know, I need Zach here to like bless me.
By mathematical authority, this is bequeathed upon you that you may
I don't know
break
if
up
I'm
the
allowed to
DRDT.
evaluate parts of limits separately. What's up, Jack? Jack in his house.
Hello.
How is the class going? Have you stumbled upon any more things that are broken in it? Unfortunately.
Yeah, I've just been going for Kudu and it's being weird, so yeah.
It is, dude. It's such garbage.
Emotional, damn it!
Oh man, I'm so frustrated. I've used it in previous years. Totally fine. Didn't have any issues. And literally they were like talking this all up all during like the spring quarter, because I said like, hey, like I'm gonna have a busy summer, like I'd like this to be like kind of painless. They're like, oh, dude, we got the thing for you, because we just completely rewrote everything and it's all super awesome and it's all gonna work and it's all great. And I'm like, all right, cool. And it's been absolutely anything but that. Every day there's something wrong that I have to fix or like report to get fixed. Oh. Anyways, what's up, Jack?
So I was going to ask, so I've been going over like the sound wave stuff in preparation for our exam, because that was like the most recent thing I went through.
Yeah, sound waves are
I
great.
just want to ask like some content questions will be covered, etc.
Perfect. Yeah, let's do it.
So obviously I know how like since sound goes, or sound waves is just really just waves that go through gas, that air. And you can like model it describing sound as like change in pressure.
Yes.
There's like this whole equation. It's very similar to like the position of a wave, like the wave motion position equation with like, there's something like that with like change in pressure.
Okay.
Should I like practice using that? 'Cause I barely ever use that. I don't even think
Derivation.
I use
Is that the speed of sound and air? Is that this one?
it's
DM.
the sound waves, number 2.
Sound wave, number 2. Where is the equation? Oh, there we go. I mean, you should know in general that waves follow this generic format of sine kx, right? Omega t and then phi. You don't need to rederive that. This is just so all wave behavior, Jack, basically follows this equation, the sine kx plus omega t plus phi. And then what they're saying is that like sound waves are just variations in pressure, but it's still a wave. It's just the pressure is what's causing the wave behavior. It's changes in pressure. Whereas, for instance, if you had like a rope that you were swinging up and down, or an instrument that you're plucking, it's actually the movement of the string that is doing the sine kx omega t phi stuff.
Okay.
Yeah.
So same thing. All right. I was just wondering because like I know the like the wave motion equation. I was just like, do I need to know how to like work with this in a problem? Same thing with like the displacement equation right below it.
I think like, you know, a perfectly valid thing is to ask like, hey, you know, if k is this, what's the wavelength? Or if I gave you like an equation of a wave, you should be able to identify like which way is it moving. You should be able to identify like what the wave speed is, and then if there's any sort of positive or negative interference with a second wave that's on top of it.
Okay. Let's see what else. I think I asked you this before, but are we going to need to know how to calculate the velocity of a wave through a liquid?
Velocity
using like
of a
both
wave
modulus
through a
and
liquid. No.
density?
No. Screw all that modulus. That's engineering talk. Yeah, don't worry about that stuff. No Young's modulus. No, I won't do that to you. You should know how to calculate wave speed from tension for sure, right? The square root of ft over mu. That
Do I
one
need to,
definitely
like-
should know.
The one right above it with like an ideal gas where it has like
Oh,
the
the
enzymatic
gamma RTK. No.
yeah.
No.
Okay.
I mean, these are all useful things, but if you're asking like, is this on the exam? The answer is no.
Okay. The derivation of the speed of sound in air. Like I see this, there's a lot of deriving and I see this. I'm just wondering, do I need to do all that and practice doing all that? Because like you just said, we don't need to use.
No. Yeah, not with the temperature stuff. No, I don't think so.
Okay, got it. Will you have like a given like what is the velocity of a wave in air, or will we have to use that 331 meters per second thing?
It'll usually be given to you. It'll be given to you
Okay.
as a number or something.
Okay, that's good to know.
You know what I'm just noticing? I'm going through the exam right now. All of my diagrams are gone. Oh man. Ugh.
Are you doing
Kudu.
it through Studio?
Kudu, you curse you, Kudu. Yeah, I mean, yeah, that's how I host the exam. That's how I host like the questions, and so like you guys can look at things and put in answers. Of course, everything you'll do, you'll also like submit like a handwritten thing, right, with your work, because in the very likely chance that Kudu fucks up, like I want there to be like a physical representation of what you submitted, so that we can individually make sure you get credit for that. Homeworks
Okay.
and stuff, I'm cool just like being like, it's not your fault, things suck, we'll give you 100. I can't do that on the exam. Like they will come after me
Okay.
with pitchforks.
Also, like I think it was like homework 1. I accidentally guessed on a question. I
It's
guessed
fine.
on a question
Full credit.
twice,
You get
and it
full
was
credit.
wrong.
You get full. I'm giving full credit to probably the first 3 homeworks at least, maybe the first 4, definitely the first 2, because that's not fair. The amount of like things that we're messing up on the first 2 homeworks. As long as you try to do them and like you're learning from trying to do the questions, that's the most important thing. I know the grades is a nice representation of the effort you put in, and it's kind of like a, hey, I did this, I get an achievement, like yay. But there are things like outside our control right now where
Okay.
yeah, like why are my diagrams disappearing now? They weren't disappearing earlier. Like what the hell?
Yeah, I was just wondering because on like homework 3, there's like a portion after you complete like the main homework questions.
Yeah, the practice
It's
questions.
like review, or like it's like shows like all the work like you've completed, and like
Yes.
it gave a strange number like 35 out of 43 completed, and there's not even 35 questions.
On homework 3? Yeah. Let me see.
Yeah.
I'm curious. So what happened is I think a lot of the back end is kind of the same. They basically vibe coded the whole front end. And the issue is that so a lot of the issues we're seeing is because the UI isn't displaying correctly what's on the back end. Is what I've like surmised at this point at like what happened. Let me see. Okay. Because damn, there are a lot of parts to this one. Okay, wait. Question. How many practice questions were there? There were 8 practice questions. Okay, 8 practice questions. And there were 8 regular questions. So it might be including the practice questions as like you haven't completed those, but those aren't due. That shouldn't be like assigned. They're not assigned to you.
Okay.
Yeah. Okay. Yeah, just y'all are doing the Lord's work, just posting in CampusWire screenshots of everything that's wrong. I appreciate that. Because it makes my job easier. Because I just constantly at this point I just invited the devs to CampusWire and I said, here are the tags, and it's your job now to look at these tags and fix things as they come in. Because I was cool with it being like a couple errors here and there, and I would like paste emails and like send it to them. But now it's like new things every day, and I'm like, bro, this is not my job. My job is to teach, not to be QA. Sorry, I'm ranting, but I'm frustrated.
All right. So
All right, what's up?
Yeah, homeworks are for grades, so yeah, that's not
Yeah,
completion.
they will be for grades when they start working more, which I hope they're working now. But again, for homework 5, like none of the diagrams are displaying now. So I'm working on getting that fixed. But yeah, don't worry about it. As long as you're like putting effort in and trying to answer things, I won't penalize you guys for anything that's not your fault.
Okay, for sound intensity, there's a
Yep.
an equation where it's like the change in volume equals the area times the displacement of the liquid. Or it was I think it was a liquid.
Yeah. Okay. Here it was. Yeah. This.
Yes, that. There's this whole long equation at the end that says
No.
you could use this. Do I need to
Nope.
know it?
Nope. Don't need to know this. This is. I mean, it's cool, but it's not on the exam. The main thing you need to know for intensity, right, is intensity is pressure over area.
Okay,
Or-
do I need to know like the change
power
in,
over area.
Pressure max squared over 2 density, the weight and the velocity of the volume?
No.
equals-
No. This one, delta P max squared over 2 rho V. No.
Yeah.
No.
Okay. There was a question on the homework to do with like the intensity number 2 equals the intensity number 1,
Mhm.
and it's like this was like with spheres and stuff. So
Okay.
then it was like the equation is you just pass it. It's in the intensity section.
Oh, sorry. It's in the actual textbook, not a homework question.
Yeah.
1 sec. Let me go find and get it. Sound intensity. Okay.
It's like, where is it? Scroll up.
Is this one? No.
Keep going. You stop.
Yes.
Like I2 equals I1 over
R1 over R2 squared. Yeah, this is important.
There was like a question that asked it, and obviously, like, I get it. You can derive for this using, like, if it's a sphere and stuff. It's just at that point, it didn't say it was a sphere.
Yeah, no, it said the area of a sphere is equal to 4 pi r squared. And so that means that the area goes as r squared.
Okay.
Right,
It's
where
like,
r is the
there
distance
was
you're
the
away.
one homework question. Where was it? I have it written down somewhere. Question number 7 for homework 4.
Okay. Is that the Sound of Music homework or a different one?
Music homework.
Okay. Yeah, this one right here. With this
Yeah, I was
diagram
confused
that
about
you
this
can't
one.
even read this diagram, dude. What the hell?
It's basically that the top half's like area or like length of travel or the travel path
Yes. Yep.
is going to grow by equal amounts of distance on both sides. So
the other key thing here is that the distance increases by twice the amount that you
Yeah.
pull it out, right? So if you pull it out, you're increasing the distance it has to do on one of the legs and also the distance it has to do on the other leg.
I got up to that point, but I couldn't
Yeah.
figure out why. So I had to look on CampusWire for this. It's the intensity 0.2 equals intensity 1, cosine squared, then pi change in r, which is like 0.2, 0.4, over the wavelength. I don't know I don't know how they found that.
Okay, let's see. That's a good question. And I apologize. This diagram is impossible to read, dude. What? Okay. So there's a source here. Okay. And then we have, right, like this. This is like one path. And then this is another path, right? But then I think this top one can move up and down, right?
Yeah.
Okay. And we said that the wavelength is equal to 1.2, okay? So right off the bat, let's just come up with some situations for like where would there be perfect constructive interference and where would there be destructive interference, right? So constructive interference is whenever R2 minus R1 is equal to a multiple of 1.2, right? Because as long as you're moving like a full wavelength, you're going to have the two waves join on top of each other at the same phasing, right?
Yeah.
Okay. And so where would you have destructive interference?
Anywhere that isn't that.
Exactly, but where would you have like perfectly destructive?
0.6.
Good. Yes. And more importantly, it has to be an odd multiple of that, right? Because if it's 2 times 0.6, then you're back at 1.2.
Yeah.
So another way to write this is like 2n plus 1 over 2 times 1.2. So this enforces like 1/2, 3/2, 5/2, and so forth. Yes. Okay, cool. And then we know that for every change in delta x, this leads to like twice the change in R2 minus R1. So I would say like 2 delta x is equal to R2 minus R1. Good?
Yeah.
Okay. So, from the original position, it moves up by 0.2, okay? So, I think originally they're equal, right? So at the very, very beginning? Yeah. Originally, you can say that, like, R2 minus R1 is equal to 0, okay? And then after A, we move it up by 0.2. So, this changes, right? Is now equal to 0.4.
Okay, yeah.
Good so far? All right,
Yeah,
then let's just do. Then it slides another 0.2, okay? So now R2 minus R1 is equal to 0.8, okay? And then it slides up another 0.2. So that's equal to 1.2, right? And then it slides up another 0.2, which is going to be equal to 1.6, okay? So from this, I can pretty instantly see, right, that this is going to be the loudest because it's the most constructive interference, right? Because it's moved a multiple of, so the path difference is a multiple of the wavelength, right?
Okay, yeah. All right. I didn't work it out this way. Okay.
Yeah. Because this is 1 times lambda. And any multiple of lambda is instantly the loudest. Okay, so let's figure out like what fraction of lambda these other ones are, right? So this is 0.8 over 1.2. So that's going to be 2/3 of a lambda, right? If you do 8 over 12.
Okay, yeah.
And then what will this one be?
1/3.
1/3 of a lambda, right? And so then this one will be 4/3. Good. 4/3 of lambda. Yeah, perfect. Okay, cool. All right, so let's consider if I have a wave. Right, let me see if I can draw something that looks a little bit better. Where this is a full lambda, right? And then this is going to be our wave on top, right? Okay. So what I want you to see is, right? Okay, so if this moves a full wavelength, it's like we just did another copy of these and we just shifted it over, right? But now let's look at what happens as we move it to the left and to the right. So if I move it backwards by 1/3 of a lambda, right? That would do something like this, yeah? Because half a lambda would be here, so actually I guess it would be something like this, right?
Yeah.
Right. So this is moving it back 1/3 of a lambda. So that's the same thing as the path difference being 2/3 of a lambda. And then by the same token, if something is at 4/3, then it moves forward by 1/3 of a lambda. Now, when a wave is at maximum, right, when they're right on top of each other, if I shift this thing to the left and to the right by the same amount, then the interference is the same. Because the interference is symmetric about being an integer number of lambdas away. We have that also from here. We derived this in here we go. Interference of sound waves.
I'll be right back.
Okay, you're good. Back, Jack?
Yep.
Okay, great. Okay, so we this is the mathematics behind this. So we derived this during lecture, right? Where this is what a new wave function looks like when there are two wave functions on top of it.
Okay, hold on. What is okay, I see the back half of it, the sign to the right of it. That makes sense. Why is the phase shift divided by 2?
Good. Okay. So that came from there was math to when we did this. Where was it? I think this was in was it in mechanical waves? I think it might have been mechanical waves. Yeah, interference of waves. Yeah. This was the derivation that comes out. It has to do with there's a half angle identity. So when you do sine of u plus sine of v, you get 2 of sine of u plus v over 2 times cosine of u minus v over 2. And so if this, for instance, is u and this is v, when these two add to each other, you end up getting 2kx minus 2 omega t, and then it's plus theta, and then that's all divided by 2. And so that's why this term comes from adding these two together. But then when you do u minus v over 2, okay, kx cancels with kx, minus omega t cancels with minus omega t, and you're left with theta, but then you're still doing divide by 2. And so that's where this term comes from.
Whenever for sine you're adding u plus v,
Uh-huh.
shouldn't that be 2kx minus 2 wt plus...
Exactly. plus phi,
Theta.
but then that's all over 2.
Oh,
you see-
okay.
So you see how the 2 will cancel here? But then you still have phi over 2.
Okay.
Cool?
Yeah.
Okay. So the main takeaway from this is I don't care about this. This is just another wave that's oscillating. This is now governing the amplitude. Right? So,
Oh, that's the amplitude.
yes. Do you see how this thing does not depend on x and it does not depend on t? It affects the entire wave at every position at every point in time.
Okay. Is this an equation I should know by the back of my head?
I think it's a cool one to know. I mean,
Okay.
you
I'm just
don't...
wondering because I don't remember using this on the homework of the clicker questions very much. So I'm like,
No, yeah, I'm trying to show here that because everything is 1/3 lambda away from perfectly constructive interference, that they're all going to have the same amount of like partial interference. But to like really convince you of that, it helps to show you mathematically why that is. What's up, Zach? Okay. So, in terms of like phase difference, okay? So if something has a phase difference, so let's say like a path difference. So let's say R2 minus R1 is equal to a full lambda. This is the same thing as a phase difference being equal to 2 pi. Or 0. Right?
mhm.
And you see how like cosine of 0 and cosine of 2 pi, it's either +1 or -1, but that doesn't matter, right? Because this is an amplitude. So it's just saying that your maximum amplitude will be a magnitude of 1. If you have, if this is equal to, for instance, 2 pi, technically you have the cosine of pi, and the cosine of pi is -1. So technically the new wave is like flipped, but the amplitude of it, right? This term, which is a number, is still the biggest it can be, right? The biggest this can be is either like +1 or -1 in terms of magnitude.
Okay. So depending on the size of the phase shift, that's what
Depends-
changes the size of the amplitude.
Good, yeah. And think about this in terms of absolutes, okay? So if this phase shift is 0 or 2 pi, then this thing is the biggest it can be. It's gonna be the absolute value of it is 2a, right?
Okay. Yeah.
Okay. Let's think about some other things. Okay, so what if R2 minus R1, so this is the biggest. What if R2 minus R1 was equal to, right? We said like pi over 2 or 3 pi over 2 or something. So that corresponds to a phase shift. So look, if 1 lambda is 2 pi, then lambda over 2 would be 2 pi over 2, so that's just equal to pi. I say, or 0, and here, let me show you. So like cosine of 0 is equal to 1. So in this case, we end up doing cosine of pi over 2, right? And that's going to give you 0. And so that's why this is destructive interference. So this
Okay.
is-
That makes
You
more
see that?
sense.
Good. Okay. All right. Now let's look at the in between. This is where this question gets tricky because I'm asking. Okay, I know where it's max. I know where it's min. What about in between? Right. So let's think of all the cases we had. We had 2 pi over 3 and 4 pi over 3. Right.
Mm-hmm.
So let's see that. So if R2 minus R1 was equal to 2 lambda over 3. Right. Then that's the same thing as this being equal to 4/3 pi as like a phase shift. Yeah?
Okay. Yeah.
I'm just taking this, I'm multiplying it by 2 over 3. Yeah? And let's say R2 over R1 was our other case, right? So we said 2/3. Let's look at 4/3. Let's look at 4/3 as
So
well.
wait, one wavelength is equal to 2 pi?
Yes, one wavelength is 2 pi a phase, for sure. Yeah.
Okay. Yeah.
So then if this is 4 lambda over 3, then this would end up being 8 pi over 3 for phasing.
Okay.
Good so far? Okay. Now, let's think about what happens when this is going to get put into this term, right? So now that's going to end up being cosine of 4 pi over 3 divided by 2. And so that's the same thing as cosine of 2 pi over 3 for like my new amplitude term. And then this is going to be cosine of 8 pi over 3 over 2, which is the same thing as cosine of 4 pi over 3. Okay? Now, I want you to think about, like, what is the value of cosine of 2 pi over 3 versus the value of cosine of 4 pi over 3? You could put it into a calculator if you wanted to, or, I mean, I like to, again, I hated the unit circle when I was in your position, but it makes so much more sense if you understand it. So 2 pi over 3 is
Wouldn't they be opposites of each other?
exactly, but they have the same magnitude. So right, if this is pi over 3, this would be 2 pi over 3, right? And then this would be 4 pi over 3, right?
Yeah.
Do you see how the cosine of these things is actually literally the same? Because cosine is the adjacent over the hypotenuse. You can also verify that with a calculator. You can say what's cosine of 2. I mean, yeah, we can pull it up. Where's my calculator? Bum, bum, bum. Wait, 1 sec. Okay. Yeah, you can also verify this with a calculator. So if you did cosine of 2 pi divided by 3, which I'm going to do that. Make sure you're in radian mode, of course, for this. I end up getting minus a half. If I do cosine of 4 pi over 3, I'm also going to get minus a half. So what that tells me here, Jack, right, is that my amplitude term for being 2/3 lambda and being 4/3 lambda, it's the same. Like, this amplitude is the same.
Oh, okay, because you take, well, are you supposed to, because like whenever I put it in to just to online just to figure it out after I couldn't figure it out.
Yeah, what'd they say?
It said it's cosine squared.
Yeah, that's for power, for sure. Yeah, if we're talking about like power, it's technically cosine squared.
Yeah.
Is that what they wanted?
Yeah. Well, it's asking for intensity.
Okay, sure. Yes, technically it's squared, but the intensity goes as the amplitude squared. So if the amplitudes are the same, then the intensities are going to be the same.
Okay. Because whenever I thought like the area, I was confused because like, is the area of the pipe like a circle or something? Because it was asking for like, whenever they had cosine and stuff, I wasn't sure like how I was supposed to find the area.
Yeah, no. I think what they're doing. So A here is amplitude. First off, I think what like whatever ChatGPT was doing is they were figuring out that y of x of t squared, that's equal to the intensity, or like the power. But then yes, you do need to also know like the amount of like area in the pipe, but that's constant, right? Because these things are two sides of the same pipe. It's the same pipe, right? Yeah. So
okay, so
that's why
this equation right here, I should have led with that.
It's just one way. So here's the beauty of physics, Jack, is that like, yeah, the way that whatever ChatGPT did it, that's technically also correct. But I think this way to me makes more sense because I have like this gut instinct of, as I was saying earlier, you know, if I shift a wave by whatever amount of wavelengths to the left and whatever wavelength to the right, if it's the same amount of shift, then I think like the interference should be the same. And then I say, okay, but what mathematical equation do I know about interference? Well, I know this one. And when I talk about shifting something by wavelength, how does that refer to like a shift in like phase? And then what I can show is that, yes, if I do shift something, in this case, this is a third of a wavelength away from max, and then this is a third of a wavelength up from the max, that I end up getting the same like amplitude term in the
I
front.
have no issue with like visualizing it. It's just
But your eyes can deceive you though, right? Visualizing can sometimes screw you. So this is where like verifying it with the math I think is really cool.
Okay.
Or I hope it's cool.
Yeah, I'll look over that question more later.
Yeah. And just real quick for the other one, because we said that like all three of them were equal, right? We said B was equal to A, which is equal to D.
The third one is equal.
Yes, because if this is R2 minus R1 is equal to 1/3 lambda, notice how this is a third of a lambda up from 0 lambda, which is another max. Right? So you have maxes at R2 minus R1 is equal to 0 or lambda or 2 lambda, okay? So when your phase shift is the same amount of lambda away from a max, so do you see here, if I go down by a third, that gets me to 2/3. If I go up by a third, I get to 4/3. And then here, if I go up by a third, I get to 1/3. It's the same amount of shift. That's going to lead to the same amount of amplitude in like the interference equation between the two waves.
Okay.
Yeah.
Let's see. Do I have any other questions?
Yeah. This is a fun one. I particularly like this question. Wink, wink. So like, I would study this one. I think it's a very cool. I think it's a very cool question.
Okay. I will. Would you say a question like this is like? Would this be a free response?
I think this might be a multiple choice, honestly.
Oh, good. Okay.
I think. I don't remember, but yeah.
Are you gonna put out like a practice exam?
Everyone's asking me for a practice exam. It just honestly, with like the pace of how the class is going and how everything is just like screwing up, I just don't have the time to create a whole new practice exam. And then students will get mad at me if like the exam doesn't look exactly like the practice exam. So what I try to tell students is that like, hey, any homework question you've done is pretty much a practice exam. Any clicker question you've done is pretty much a practice exam. Anything you've done in discussion is pretty much a practice exam. If I didn't have to compress everything into 6 weeks, and if I wasn't dealing with like 5 new kudu errors like every day, then yes, I would totally have the bandwidth to create a practice exam for this class. But things just move so quick, I just can't.
Okay, got it.
Yeah.
Let's see. There's like stuff in Hear It and Pitch. It brings up stuff like fawns. Like the second you
Fawns?
hit.
Wait, Fonz? Like the character from like Cheers? Wait, what's the Fonz?
It's just a unit used to express loudness.
All right, give me, what chapter is that? That's in
Hearing and Pitch, number 10.
hearing and pitch, hearing loudness. Decibel is all you really need to know. Oh,
Okay.
fawns. Dude, what? That's hilarious. No, you don't need to know fawns. Did you ever see a homework question with fawns on it?
No, I just
Yeah,
didn't
it's-
think. Yeah.
I mean, it's cool. Again, I implore you guys. I don't know. What do you? Here's a good question for you, Jack. Why are you taking this class? Are you a physics major, engineering major, pre-med?
I'm engineering, yeah.
Engineering. What type of engineering do you want to do?
I'm mechanical.
Cool. So, I mean, this class isn't as... If you said electrical engineering, I would say, like, you should eat up everything in this chapter, in this whole course, because this is very related to electrical engineering. For mechanical engineering, more of, like, 1A is kind of what you really liked, and then, like, maybe 1C. But, yeah, stuff like this is very interesting to know, But in terms of, is it going to be on the exam? Again, if it hasn't showed up in the homework, if it hasn't shown up in a clicker, it's not going to be on the exam. So if I've never talked about fawns, I honestly didn't even know what a fawn was until today. So it's not going to be covered. The textbook has more material in it than I can cover in 6 weeks. But it's good for you to go through it. I'm glad you're going through it, Jack. It's cool.
So whenever you have resonance in a tube closed at one end,
Yes.
obviously I know what a standing wave is when it's just like a wave that just has changing, or like not changing, but like inverse amplitudes, but no propagation speed, right?
Mm-hmm.
There's like an equation in chapter 15, where it's like the position of the resonant or whatever is equal to 2a sine
KX.
x. Do I need to know that?
It's useful. Do you see how this is also basically kind of the same, like, phase shift equation almost? Like, there are points X, right, where I don't care what happens in time, the thing will never be oscillating.
Okay.
It's almost like destructive interference in space. Right, so if you look at this, right, this is, I guess, right, a standing wave per se, right? So what this describes, right, is that like at x, or at, for instance, like kx is equal to n pi, right? Because sine of 0 is equal to 0, sine of pi is equal to 0, and so forth and so forth, right? You have nodes, right? Yeah, these are nodes. Because this entire term here, right, Jack, just goes to 0.
Mm-hmm.
And so now there's no amplitude at all in time, right? And so this is a cool way, and remember that k is equal to 2 pi over lambda. So you have 2 pi over lambda x is equal to n pi. So pi's cancel out. And so that tells you that x occurs at n lambda over 2. So you can either have, so the location of your nodes will always be at like some half integer of lambda. So in the case of, what is it,
Yeah,
like
there's
this?
an equation for like finding the nodes of something.
Right.
Do I need to like know that equation by heart? Or should I know that equation?
You should know the diagrams, right? So you know, right, for this is like x equals 0. This is like x is equal to, what is it, like lambda over 2? Do you see how that corresponds to 2 nodes, right? It's when like n equals 0 and then like n equals 1 for this.
Yeah.
Right? Yeah. And then you think, okay, well, what's another way that I could have nodes at either end? Well, I could have this. And now you have 0, half, full.
Isn't
And
that
so-
a whole...
That's a whole wavelength, right? Yeah.
Yeah, it's a whole wavelength.
You see how this is 0, this is lambda over 2, and then this is like 2 lambda over 2?
Mm-hmm.
Yeah. So this equation is cool because it shows you where the location of the nodes are. This is also really easy to just kind of reference a table. What is it? Closed, standing modes. What diagram do I like to use? I guess this one's kind of cool. Yeah, this is okay. Yeah. So something like this can be very handy to understand what all the different harmonics are. So maybe having something like this would help on an exam, right?
Yeah. Well,
I don't think I don't think I have this on the equation sheet for you, but you can always just like reference this. You know, I say like the exam is supposed to be closed notes, but I can't prevent anyone from actually making it closed notes. I'm not gonna like check webcams. I'm not gonna do like all this stuff is garbage, and everyone can get past it. So if you need to like look this up and reference this, it's okay. Like I totally understand. The better like practice as a physicist is to be able to come up with this yourself, to to be able to like on the fly. But I understand if like you're getting like a super like brain lock, you're like, oh man, I don't know it at all. You can kind of always just like look this up and reference it. But
Okay.
this is kind of like it's cool. You know, this is like F1, and then this is like 2F1. This is like 3F1, and then this is 4F1. So, yeah, that all comes from this equation showing that where you would have nodes. And then also, whenever this is a maximum, right? So whenever kx is equal to 2n plus 1 over 2 times pi, you have antinodes. And because what that does mathematically, right, is that jumps this thing to either plus 1 or minus 1. So it makes it like the biggest it can be. And then so in time, the wave will oscillate with its maximum amplitude there. And that's why with standing waves at like these locations, you see the wave jump from like up here to down here the most in time. Yeah.
Okay.
That's why I like this chapter, because I don't know, there's like physical phenomena, but then if you run the math, it also like validates itself and it makes sense, and you're like, yes, physics is not a lie. With the power of math, we can prove things are real.
Okay, then for question number 2 for this chapter?
In the homework?
Yeah. I eventually was able to solve it. It's just like the way it was worded, I was confused because it was like it made it sound like we were like hitting the pipe at like 1/4 of length from one end of the tube.
Mm-hmm.
And I was like, okay, would that would still technically be 2 open ends, but I was just like, that'd be weird because you'd only have 3/4 of a length to work with for.
So yeah, when you hold it somewhere, you're enforcing there to be a node there because you're not allowing it to vibrate there.
Oh, that makes so much more sense.
I know. Yeah, this question's kind of worded weird. So, for instance,
I
Yeah, go
didn't. Well, I thought if you like, you know how like on an open pipe with a closed end,
yeah,
like let's say you like blow into it, right?
yeah,
With you blowing it from the open end, right? That technically in my head, it's like since it's open, it's gonna have an amplitude. So
at the open end for sure. Yeah.
So I was like, technically, if they're both open ends, or if we're assuming they're both open ends, they should both have.
Yeah, they should have antinodes there. Yeah, but remember that open follows the same pattern as closed. So, I see. Because you thought this was closed opened from the point where you're holding it to the other point of the rod, right?
Well, I thought no. From the point I was holding it,
yeah, I
thought it was open, and the point at the very end of the rod was also open.
Ah, okay. Yeah, no. So, 1/4 from the length, right? So that means you're holding it at 20 centimeters, and that means that there's a node here, per se. Okay.
So there's a node. I thought if so, are we treating that as like where it's open or is it closed?
So, so the entire thing is vibrating, right? You're not suddenly gonna have like no vibration here or like no vibration here. The whole thing is vibrating.
I thought wouldn't the epicenter be at that point? So would you have like 2? Or I guess since both sides are open.
Both sides are open, right?
It isn't gonna like come. Well, it won't come resonating back to you, right? Because if the sides are open, the waves will go out into the atmosphere.
Well, yeah. So if you hit this, anytime you hit something, right? There's a natural resonant frequency that it wants to vibrate at. Mm-hmm. In all seriousness, when you hit something, it vibrates at a ton of different frequencies, but only the frequencies that match the geometry of the object with like open on both ends and nodes here and here. Those are the ones that vibrate the loudest or the most because they reinforce themselves. Ones
Okay.
that don't fit that will constantly be out of phase with each other, and so they constantly like break each other down.
Okay, so the pipe, right?
Yes.
We are hitting the pipe 20 centimeters from one end.
Mm-hmm.
That is a quarter of its length. Whenever
Yeah.
we hit the pipe at that point, the waves, or I guess like the vibrations that we cause by hitting the pipe at that point spread out from that point, right?
Yes.
So
Well, no. Sorry. We're not. I don't think we're not hitting it at the node. We're hitting the entire pipe. So you see how it says the student strikes the lab. We hit the whole thing. We're not hitting it directly at the node. We're just holding it at the node, and so we're enforcing that there has to be a node there.
Oh, okay. So that's why. Oh, okay. That's why I was confused, because like in my head, I'm like, you're hitting it at this exact point. So the vibrations would start at that point. So the vibrations would be going both
Yeah, no.
left and right. So
So you're hitting it right at a quarter, and then again, if this is an open pipe, right? Which situation does this look like, where you have it, where you have a node at a quarter?
a node at a quarter.
So this one has a node just at a half, right?
Would it be?
I think it's this one, right?
Yeah.
I feel like it's this. And you could solve for this, right, too, right? If you wanted to do the math, whatever here, having antinodes, there's probably, I think, is this the equation just specifically for closed?
I think so.
Yeah, so it's probably a different equation for like open closed, but here's also the main thing, right? So, for open, it has like the same pattern where the whole lambda, right? The whole length is a lambda. And so if you have a whole wavelength fitting in L, that means halfway through it will be an antinode. And then halfway from halfway, which is a quarter, that will have to be a node.
Because each wavelength, or like let's pretend one length has one wavelength in it. That should be, there should be 3 nodes and 2 antinodes, right?
Yes, depending on how it works, right? So if it was closed, right, that would look like this. So that would have 3 nodes and 2 antinodes, right? That's one way to fit a full wavelength in, but that's if it's closed. If it's open, right, you need it free on one end, and then it needs to be free on the other end as well. But it has to return to its original position. So in this case, you have antinode, antinode, and then so halfway in between these has to be node and node. Just by symmetry, right?
Yeah, so like one wavelength has to have like some sort of combination of like
3 and 2.
antinodes or 2
Yeah.
antinodes.
Yeah,
Okay.
exactly. So that one fits this, right? Which, for that case, so we can probably like draw it, right? We can say like, okay, cool. That's like this, and like this. And so this would have been another node. We know that L is equal to a full lambda there, right? The length is 1 full wavelength. So then what's the lowest what's the frequency of that, right? What's the frequency that can happen that? Well, I know that F lambda has to be equal to C, which I think is what, with 343 probably, right? Because I assume they're sound waves.
So wait, just wondering, going back to
Yes.
the original question. So if I were to strike this pipe 20 centimeters from an open end, right?
Yeah.
Would the vibrations start at that point?
So when you hit it, the vibrations would be everywhere. First off, well, the vibrations would technically be where you start it, but the standing waves that would survive are the ones that either look like this, or the higher order ones. Like this one would survive, this one would survive, this one would survive.
Okay.
But the case where I'm enforcing a node to be at a quarter, that means I think only this wave really survives.
So
because
whenever you're squeezing the pipe, you're forcing the node to be a quarter of the length from. Okay.
Yeah, I think this one would work as well though, right? Because you see how this
Yes.
one has, or maybe it wouldn't actually. Sorry.
I don't think it would.
One version where it's higher than this, I think you can eventually get another case where you basically double what's happening, but you still have a node at a quarter. And that would be a higher frequency.
Wait,
You see how these are higher frequencies than these?
How would you do that? Because if you have, like for number 2 with the second harmonic, if you want one node at it of the length away, for you to have another node a quarter of the length, well,
I think you could. I think you do this by like a factor by 4 or something, right?
Like 4, or like
Yeah.
5 or 6. You basically have to get. If you
Like
wanna,
look for example here. If you have a node at halfway, you can have it happen again by basically splitting these two into 2 again, right?
Yeah.
But the key thing is that this happens at a higher frequency than this one. And the question was asking, what is the lowest frequency? So they want the most basic mode that this happens at.
Yeah, but if you want to get at a higher frequency, you still want a node at a fourth of the or
Correct.
a quarter of the length.
Yes.
So if you're working in a quarter, you would probably want to get like, if I don't know, I guess if you want, well, I mean, if it's open length, you're going to have anti-nodes at the very far left and very far right.
Exactly.
So, I mean, if you still want a node at a quarter, then you'd still, to make it symmetry, you need one at 3/4. So I guess you could do it where you have like one at every
One of every
1/8?
eighth, maybe.
one
Yeah.
at every 1/8, yeah.
Yeah, because I think you'd have to do like something like this, and then like this, and then it would have to hit like that. Yeah. Do you see how this is? This is like a quarter of a wavelength that's being shown there. I think you'd need an eighth of a wavelength to be fitting in there, or maybe even more. I don't know. Don't worry. I'm not gonna ask you about like what's the next highest one or something.
Okay.
Yeah.
Okay, yeah. Let's see what else.
Would we get the right? Sorry, let me make sure we would have gotten the right answer there. Sorry. Because I said that.
I didn't. Where I struggled initially was I didn't know that point was supposed to be a node.
Yeah.
Is
Oh,
that
you know
like-
you know what's another thing that's not given in this question?
What?
You need to know the wave speed in aluminum. They didn't give this. in
Yeah.
the
Oh, yeah. That wasn't given. I had it.
yeah, because I was like, is this sound waves? I'm like, bro, this number isn't gonna work out. Yeah, no, this has to be. I think it's like 5,000 or something, right?
Yeah, it's 5,200.
Okay. So then you have like, okay, F times 0.8 is equal to 5,000. And yeah, that'll get you basically 6,400 once you divide by 0.8. Yeah, 10 over 8. I think so. 50,000 over 8. Yeah, basically 6 point something. Got you. Okay. Cool.
Okay. Yeah, that one was confusing for sure.
Mm-hmm.
Let's see where else. Number 6.
On this homework?
Yeah.
Oh,
A
yes.
plane's flying at Mach 1.2. And long story short, and once you do a trig problem to solve for the different in the altitude the plane's at compared to the observer.
Yeah.
And so like I figured out like obviously Mach equals the velocity of the plane over the velocity of air.
Mm-hmm.
And using the given velocity of air, I solved for the velocity of the plane. So I was able pretty quickly to get that far, and then I was able to find the sine theta, which is just equal to 1 over the Mach.
Yeah.
And I got the angle of 56.44,
Okay.
but I think I must have drew my diagram incorrectly because I had to swap around my equations and stuff
All good.
to get the correct answer.
Let's see. Yeah, let me get a nice diagram for this one. Someone's already done a diagram. I'm sure they have. Where's the diagram? Okay, I guess this is the best we got. Okay. So you have this, right? Yeah. So you can get what the Mach angle is. And yeah, Mach angle is equal to the arc sine of 1 over the Mach number. Okay. So you get that theta is equal to arc sine of 1 over 1.2, right?
Yeah.
Okay, cool. And what'd you say? You said that was 54 degrees?
Yeah. 56.
Let's double check.
Because I.
So someone in my chat was like, "Today I learned Mach angle is a thing." Yeah, Mach angle's super cool. I hope you guys enjoyed. It's one of the cooler things in physics, and I usually never understood it. And it's only been recently that I've taught it like so many times to other students. I was like, "Ooh, I think I can explain this to people now." So I don't know if it made sense when I taught it, but I hope I was like kind of there. Okay, so this is 56 degrees, correct, right? And we're saying that they hear the sonic boom 15 seconds after the plane is directly overhead. Okay. So the plane was here, right?
So wait, hold on. Is Mach angle? I thought Mach angle was just like the angle between the or like the velocity of the plane and the velocity of the wind beside it.
Yeah. So Mach angle is the angle between the velocity of the person and then the wave front that's sweeping the ground. I also have a 1 sec. I have a picture for this one. I saved this in my notes. I remember seeing this. I was like, this is a great diagram for Mach angle. Oh, wait, Mach. Yeah, here we go.
Wait, you don't write anything down after conversations?
Okay, 1 sec. Oh, look, AI slop ads. Great. Okay, here we go. Okay. Okay, so this thing's generating sound waves, right?
Mm-hmm.
And then do you see how there's this like diagonal wave front that passes, right?
Yeah.
Okay. So Mach angle refers to the angle made between the wave front and also the vector of you traveling, you traveling, sorry. Yeah. So this right here, this to this, that's Mach angle. And where that comes from,
So
right?
is the horizontal angle that, or the horizontal arrow, is that you or like the plane or?
This is the plane,
Okay, and
and then this is
we're
like the
assuming that
sound wave.
sound waves. Oh, I thought that was just supposed to be air.
Well, I mean, like whatever pressure waves, whatever's causing like loud things to happen, because what's happening is, so your velocity here, right?
Mm-hmm.
This is v times t, and then the distance that the sound wave travels, right? That's this, and that is that's the speed of sound, which they're calling a. That's a times t. Okay. So do you see how this makes a right triangle?
Yeah.
Okay. And so if I want to figure out this angle,
Why is the speed of sound? Why is it at that angle from?
because
the-
yeah, this is very cool. So in the amount of time it takes for me to travel this far, the sound wave I generated here will travel this distance. So it'll be its speed of sound times time. And it just so happens that like as we keep generating these sound waves, they all end up colliding at this one front.
Okay, so as you are going extremely fast for a period
Yes.
of time, you go that far and you make a sound. Or hold on, well, let me think. Assuming you are faster than the speed of sound at that day,
Mm-hmm.
you guys are going very, very fast, and you guys go for the same amount of time, let's say, since like you broke past the speed of sound, right?
Sure.
And like everyone's speed is constant or whatever. You're gonna travel a larger distance than that initial sound wave.
Exactly.
The speed of the sound wave is just the speed of sound. So speed of sound times the amount of time you've been flying, and then it's the velocity of the plane times the amount of time you've been flying, and that creates two distances, and you can make an angle from that.
Yeah. So maybe this will help you. So when I generated like this bubble, right, when I was right here, in the amount of time it took for me to travel here, which was T1, I traveled this distance VT1, okay? V is my velocity. The sound wave expanded out by AT1 in this direction, right? Because that's the radius of the sound wave.
Mm-hmm.
Now, I created another sound wave here, for instance, right?
Yeah.
And that sound wave, right, from me to get to here, that's like VT2, right? That's a shorter amount of time. But also, the wave developed in size by AT2. And so, the phenomenon that's happening is that all of these circles that I kept generating are all hitting this diagonal line at the same time. The sound waves have been alive for different amounts of time, right? The ones further back here have been propagating for a lot longer than the ones closer to here. But at a single point in time, they all line up.
Okay.
Maybe this video helps. You see how like I create wave propagates, I create wave propagates, but somehow like every single wave I'm creating is all meeting up at this diagonal line. Yeah. If I'm going faster than the speed of sound. The green one here is subsonic. So I'm not as fast as the speed of sound. Do you see how none of these waves are colliding together? They are compressing. There is a Doppler effect, but there isn't all these waves joining the same wall and just like smacking things. Yeah.
Okay.
It's a hard concept. Don't get me wrong. Like this is something that when I first started teaching it, it made no sense to me, but I understand it now. So I hope it starts to make a little bit more sense for you now.
Okay, and those shock waves are generated by whenever something is going faster than the speed of sound. It just hears sound, correct?
Whenever something's going faster than the speed of sound, the waves that are generated behind it bunch up on this wave front, which is diagonal. And it's very, very loud. Because think of it as like, it's the most like perfect constructive interference you can get. Because you have all the waves before you are all lining up on the same line at the same time. So it's like a bunch of sound waves you created are all positively interfering at that point, and that creates the boom that you hear if you're just a person just chilling down here, because you hear that wavefront like swipe over you, and it's like getting smacked in the face with a bunch of pressure. Yeah.
Okay, I understand. Okay, length of VT and AT and all those smaller. Okay.
Okay.
So would the distance of AT1 be like, not like exactly, but would it be like similar or like proportional to like the distance of AT2 and like AT3, etc.?
Exactly. So AT1 over VT1 is the same thing as AT2 over VT2.
Okay, so it's similar triangles.
Yes, they're all similar triangles. Yeah.
Okay, I'm assuming, are they like, is the like the line, like the big old barrier of sound waves, right?
Mm-hmm.
Is that perpendicular to like the little individual like AT1s, AT2s?
Yes.
Like
Yep.
perpendicular?
Yep.
So whenever you're like solving for the Mach angle, are you solving for the angle like right at the tip using I guess the adjacent and the, or no, I guess should be using the
opposite
hypotenuse.
hypotenuse.
Okay.
Right. Do you see how arc sine in this case is opposite of hypotenuse? So that's AT over VT, which is A over V, which is equal to 1 over M, right? Because Mach number is velocity over the speed of sound.
Okay, yeah. So then, okay, what did I do wrong there? Because so what I did in my problem was my graph wasn't quite as like detailed as that, but I got to the correct angle for the angle equals 56.44, right?
Sure.
And so what I tried to do was use tan theta equals opposite over adjacent equals. I think I had on my diagram that was the distance traveled by the plane during the change in time over my altitude.
No, so okay, if this is the angle theta, right? Then this is the adjacent, which is the amount of distance the plane has traveled, and this is the opposite, which is the height the plane is above you.
Yeah, I think I was trying to solve for the angle closest to the ground.
Oh, okay, I see. You were doing this angle? Should be the same as this one.
I was just using that angle because that's what I did in math.
Well, it's fine because this is a transversal. If you have two parallel lines and a transversal, this angle technically equals this one as well.
Well, at this point, I didn't know what my my hypotenuse was.
I see. Yeah, totally. Yeah. And you won't know, right? You're going to use tangent. So, tangent, even if you did it at this angle, this is totally cool, Jack. You could use this angle as well, okay? This is still your altitude. And this right here is how far the plane has moved away from you horizontally before you hear the boom of whatever that wave front hitting you. Let me get another picture of this, right? So remember, right? If this is plane, and then this is you, right? Technically, you saw the plane here, and the distance it traveled, right? That was equal to VT, okay? So I know what this distance is. I also know what this angle is, right? I know this is my, like, 56 degrees. So then I can figure out what the altitude is. And you could also do that if you wanted to draw the triangle this way. It's the same thing, right? It's still, this is the horizontal distance, and the altitude is still the vertical distance. So this is where I think tangent of 56 degrees is going to be equal to the opposite. So that's the altitude over the adjacent, which in this case is 1.2 times 343. Because that's the velocity, that's v. And then times the time, which was, in my case, 15 seconds. And then you just move that over and you should be able to solve for it.
Okay.
I think. A second, let me move this over. Let's see if I get the right answer. Because I remember when I was first doing this question, I also was getting like the flip answer, and I was like, man, like, do I not know how to do trig? What's going on? Okay, times 15.
Okay,
Yeah,
I was just solving for where I messed up was I tried solving for the angle correctly, but I just thought the angle was in the wrong place. That's my fault.
Got you. All good.
Okay, that makes sense.
All good. Okay.
Okay. Okay, that's not my questions for homework 4. Are you planning to get the equation sheet out this week or tonight? I mean.
The equation sheet should have been posted. Oh my god, they just did an update to Kudu. And now my diagrams are showing? Oh man, I don't know what's going on here. These people, dude. Yes, the equation sheet is posted though, by the way. It should be in the whatever the module. Let me see if I can go find it, sorry.
Okay.
261. Let's see. Let me go find it for you real quick.
Oh yeah, I see it now.
Okay. Yeah, at the very end. So what's gonna happen is like, I would prefer you guys to like put your work down on that PDF just because it makes it easy to like find things. If you're doing it on your own stylus thing, that's cool. Maybe do me a favor and try to copy paste it into the right areas in the boxes. But then the equation sheet's at the end.
Okay, got it. Do you know? I emailed and I asked the TA if they're gonna put their the solutions for the discussions on.
What'd they say?
They said they were, but I emailed them last week and they didn't respond. And I asked them today and they said they'll put it on there. It's just that was
Okay.
like 7 hours ago.
I'll go.
I'm not trying to be pushy.
No. You should be pushy, dude. Well, that's a fucking week. If you don't do something in a week, that's a little. That's like no.
Well,
I understand.
I think I used the right email. I don't know. I used the email off the syllabus.
You're okay. No, you're totally okay. Oh man. All right, you let me know, Jack, if you have any other questions about things.
I think that's it for now. Are you having another office hours tomorrow?
I will post about it tonight. I'll say more office hours tomorrow.
That's dope.
I'm sure people will come by.
Got it.
But
Thank you very much.
You're very welcome, Jack. Take care, dude. Oh, nice. That was a good example of office hours. He asked a lot of good questions. He asked a lot of questions on specific homework ones that I do end up putting on the exam, which I think is pretty cool for him. He kind of figured out which ones I'm gonna put on the exam, and that's out of like 20 or 30 questions. But I mean, it's no surprise they're the harder questions on the homework. Anything that's like kind of difficult and students got wrong, it gets put on the exam. Yeah. Oh, I just saw your message. Sorry, Zach. Is that A of T? Yeah. It was A times T. Let's see. This one, I think we were doing kind of like some limits, right? I was showing that this was equal to 0 over 0. I take the derivative. Yeah, -1 over -1/2. That's equal to 2. So now I need the limit as x approaches 1 of all of this mess. So -ax plus sine of x minus 1 plus a all over x plus sine of x minus 1 minus 1. I think that needs to equal 1/2, right? Because we already determined that this limit's going to turn into a squared, right? So if I need something squared to equal a quarter, then I need the thing unsquared to be equal to a half. Okay, this is still 0 over 0. So I think we're going to take another L'Hopital rule, right? Because this is still as it stands. This is still 0 over 0. So let's take a derivative. So that's going to give me, with respect to x, right? So that's going to give me -a. So L'Hopital. -a, derivative of sine is going to be cosine x minus 1. A is a constant, that's 0. And then derivative of this is going to be equal to 1 plus the cosine of x minus 1. And now if I plug in 1, I'm going to get -a plus 1. So, yeah, that's cosine of 0, which is 1. And then this is going to be 1 plus cosine of 0, which is also 1. So I'm going to get -a plus 1 over 2. Okay, so wait. What is the largest non-negative integer? Okay. So 0 would work, right? Right, if this has to equal 1/2. Oh, I guess, but it was it squared. Oh, so it could be negative 1/2. Right? Yeah, this could be plus or minus 1/2. Oh, okay. So then if A is equal to 2, then I get negative 2 plus 1 over 2, which is equal to negative 1/2. I think A equals 2. I think the answer to this is... Kaushik Techno, is this correct? Is the answer A equal 2? This is kind of a cool question, actually. This is one of the better ones you've submitted, Kaushik. Let's check on chat. Kaushik says it's not.
Emotional, damn it.
Damn it! What'd I do wrong? I feel like I was on a good path here, dude. I feel like I was on a good path. It says it's not 2 though. Well, okay. ChatGPT says 0 or 2. However, as when A equals 2, the base approaches. Since the exponent is generally irrational, the real value power is not defined. Dude, what is this, dude? What in any punctured neighborhood? Okay, so apparently A equals 2 is invalid. Kaushik, put A equals 2 back in the original. Okay, sure. Oh. Well, wait. Okay, let me see. You're gonna say negative 2x plus sine of x minus 1 plus 2, right? All over x plus sine of x plus 1 minus 1. So as x approaches 1... Or sorry, this is x minus 1, sorry. I don't know that I see the issue. The base approaches is negative 1/2. Since negative a plus 1/2 squared equals a quarter. Okay, one sec. I think you're saying that this goes away, this goes away. I don't know that I see it, dude. 2 minus 2x over minus 1. Oh, I see. You're going to say the limit. Okay. Oh, I see. So then that becomes Yeah, -2/1. Oh. Okay. And that squared is not equal to a quarter. Bum, 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 bum. Oh, what? No? Huh. I don't think I see it. And is negative near x equals 1? Yeah, I agree with that. Yeah, sure. Yeah, that's from this. I agree. Oh. Well, wait, no. As x approaches 1... It's something less than 1, I guess. And this is 1 plus something less than 1. It approaches 2. I agree. We answer the exponent 2 is not actually 2. It approaches 2 because of the limit. Oh, I see what you're saying. You're saying that it won't actually be 2. So... And the only way for this odd number to turn even is if it's exactly 2. Okay. Got you. That's a little semantic. Approaches. So you can't have negative numbers? Got you. I don't know, man. That's kind of like that's just some math trickery there. That's like a little asterisk. Okay, I get it.
Yeah.
Okay, cool. All right, I think that's it for today. Let's close out the stream. All right, thank you everyone for the questions today. Appreciate. Thank you, Kashik Techno. That was actually kind of a cool question. I'm a little like, whatever with the semantics at the end, but you are right. You are right. Anyways, okay, great. So, I will have an office hours tomorrow for the UCLA kids. So if you want to come by and learn some physics, I'll put it on the streaming calendar. For now, I'm definitely scheduled for teaching tomorrow. Zach has an E&M class. Go check him out. He's a cool friend of ours. I am trying to do a chess tournament on Friday, but I literally got a notice yesterday that I got to go to San Francisco for like an all-hands meeting for this company I work for. And so I might be flying out Friday at this point, just because it's on Monday, and I don't really want to fly out Monday morning. Well, the meeting's at Monday at 9 a.m., and I don't really want to fly out on Sunday. I'd rather just get there Friday and just coast, but I'm going to see what's going to happen. I'm going to see what's up, but thank you again for hanging around, learning. I know the summer's kind of a weird time, and honestly, I do kind of feel like stretched to my bandwidth dealing with all the errors that this textbook has on this UCLA class, plus my other job, plus, you know, the streaming, plus everything else. So, but I appreciate you guys being around. Things will chill out once July is over. Then I won't have any more of this UCLA nonsense to deal with. Yeah, Zach, right? Zach, you want to know the big surprise there is that the errors are in the textbook because they vibe coded the back end and everything.
Oh no.
Get your ass on.
Yeah, it's one of these things where the person was like, yeah, AI is great. We've been using agents to like recode everything. We did everything from the ground up using agents, and it's great. And I'm like, okay. And now nothing works. So it's more than just a textbook. It's like my platform for assessing students just doesn't work. It's always the vibe coders. It's like, yeah, no, I 100% agree. Zach, I agree with you. Vibe coding is garbage if you're doing anything that requires there to not be any amount of errors. Like if you don't want any bugs, if you want things that need to be bulletproof and they're very complex, intricate systems, such as a whole like textbook, you know, homework, clicker, integration, grade thing. Like this is a very complex beast. For building something just like, you know, the queue system I have, it works. Like vibe coding's great. I didn't have to hire a developer. I didn't have to spend hours doing it, and it gets the job done. And if it breaks, which it has a couple times, we find quick ways to fix it, but it's not impacting a professor trying to teach a class.
Oh no.
Again, if I wanted to release my queue system thing as a standalone app for other people to use, I would 100% give this to like some professional coders. But at least with the vibe coding, they can see like what the function should be, and they could pretty easily like mimic it and code it like to be bulletproof. Yeah. So it impacts me. Now you keep fighting the good fight, Zach. But yeah, this has really opened my eyes up to firsthand why you should not vibe code like enterprise level applications, or like things that are used by hundreds or thousands of people in situations where you know, having even like 1% of something going wrong, like really like 1% downtime is like really bad. What's up, Fook Life? That's a funny fucking username. It's not called Microslot for nothing. Yeah. They're no longer forcing me to go to Windows 11, right? Because they realized they wrote Windows with slop. But yeah, Zach, if you ever want to, yeah, I'll give you the source. I'll give you the GitHub repo if you want to like see the functionality of the queue system. If you want to build, I know you were working on your own at some point. I remember you had like a queue thing. But if you want to see kind of like the gaming aspects I have to it, I think it's pretty cool. Anyways, yeah, let's go raid a channel. Yeah, 16, nice. Yeah, you got 16 on Friday, right? I saw that on the calendar. Yeah, make sure everyone go check out Zach's stream on Friday. If I'm not on a plane, I'll come by to this. I'll come by to your 16 thing. That sounds fun. Yeah, 16 is your baby. Or one of your babies. I know you have actual like children.
Oh shit, not good.
That you also have to take care of. All right. We're going to go raid Ask a Scientist Gaming. This is a cool guy. He, I think University of Florida maybe. But they always have fun guest stars on that play video games and talk about their work. So go say hi to them for me. Otherwise, we'll see you tomorrow. I hope you guys enjoy the rest of your Wednesday. Peace.